Hey everyone, today we're going over the fundamental theorem of algebra and the factor and remainder theorem. So the fundamental theorem of algebra states any polynomial of degree n has n roots. So if I have something to degree 4, that means it has 4 roots. Now the roots could be real or complex roots, right? Any real roots will show up as your x-intercepts, as your zeros in the graph. So let's take a look at an example here. Let's say I have 2x cubed minus 6x squared plus 3x plus 12. What I want to do is I want to look at the highest degree, right? That determines the degree of the polynomial. Over here, the highest degree is 3. So knowing that, I know this is a polynomial of degree 3. That means it has 3 roots. 3 roots, all right? Now, they could all be real roots, or they could all be complex. Well, it's a cube, right? So at least one will always show up as a real root. All right, let's take a look if we have 3 real roots, or if we have 1 real root, or 2 real roots and some complex roots. The best thing to do is now graph the equation. So let's take a look at this graph. I have 2x cubed minus 6x squared plus 3x plus 12. Even if I zoom out in the graph, as you can see, this graph only hits the x-intercept one time over here, right? Over here, almost a -1. Not quite, but almost a -1 hits the x-intercept. So that's one real zero. So I can say this has one real zero. So that means it must have, since there's 3, it must have two imaginary roots, right? One real zero, one real root, right? And 2 imaginary roots. So that's usually how you can dissect some of these problems. The key thing to understand for algebra 2 is you want to know the basic parent graphs, right? You want to know the basic parent graphs and what they look like. So the 3 key ones are the quadratic, right? Quadratic, where the highest power is 2, so x squared. So these graphs look like this, right? Or they can look like this. These graphs, so they're of power 2, and they can never intersect, or they can intersect twice, like over here and over here. All right. And then the other one you want to get familiar with is the cube root, x cubed. All right. So x cubes look like this, right? Something like that. All right. So you could really only have, you'll always have either one real root, an x cubed. You'll always have one real root because it'll always cross the x-intercept. Or you could have 3 real roots or 2 real roots, right? You could have 2 real roots, right? Boom, right? And if there's a bounce here, that means there's only 2 real roots, right? And this bounce here, when it bounces, this root happens twice. And the last one you want to get really familiar with the shape, is the x to the 4 graph, right? X to the 4 looks something like this. They look something like this, all right? They can even look on the graph, surprisingly, they can look like parabolas, right? It's deceptive, but they can look like parabolas. So they can look kind of like this, right? They look like that, but it's still making a W shape, like if you zoom in over here, right? So they can kind of look like this, right? All right, so they can have no real roots, like here. They can have 2 real roots over here, right? Or 2 real roots over here and here, all right? Or maybe you get all bounces, right? Boom, boom, right? These 2 bounce, 2 real roots, they happen twice, right? So you have 4 real roots on this last one. So you want to get familiar with these graphs, these types of x squared, x cubed, x to the fourth. So if you see a question like this, let's say you are asked, say there is a function f of x equals x cubed plus 3x plus 7, right? And then they give you a graph, right? So this is a common type of question. They'll give you a graph, right? And they'll give you g of x, the graph of g of x here. Something like this, right? They'll give you the graph of g of x here. And then they'll ask you, right? Well, let me draw the graph first, right? They'll give you g of x. Maybe they'll give you something like this. All right? Maybe something like this. And then they'll ask you to describe the zeros, right? What kind of complex zeros, right? Which function has more complex zeros, all right? Slash roots, right? Maybe a question like that. All right, first things first, let's identify some things here. If we see a question like this, right? This one, they give us the graph, so we don't have to graph it. But this is a W-looking shape here. So I know it's some x to the fourth function, all right? X to the fourth function. And how many times does it intercept the x-axis? Intercepts here and here, and it doesn't bounce, right? So these roots only happen once. So I can say this one, g of x, has two real roots. Two real, right, roots, right? It's supposed to have four roots, right, because it's x to the 4. Since it has two real roots, that means the remaining are the complex roots, right? So this has two complex roots. All right. For this one, for f of x, we know there'll always be one real root because it's x cubed. But let's try to graph it. See how many roots we get, right? Let us graph this. So I have x cubed plus 3x plus 7, right? So x cubed plus 3x plus 7. So I can see it only intercepts the x-axis one time, right, over here, very close to, in between -1 and -2. So this has one real root, supposed to be of power 3, so it has 3 roots. That means it has 2 complex roots, all right? So this one has one real root, f of x, right? And that means it has 2 complex for f of x, right? Which function has more complex 0/roots? Well, they both have 2 complex roots. So we say neither. They both have 2 complex roots. All right. So let's move on to the factor and remainder theorem. So the factor and remainder theorems, they state, right? They kind of lend themselves into each other. The factor and remainder theorem are related in that one is kind of derived from the other. The remainder theorem says when we divide a polynomial f of x by some factor x minus c, the remainder is f of c, right? And the factor theorem states we can say that x minus a is a factor of f of x if f of a equals 0, right? If it's a factor, we know it hits the x-intercept, and we know the y there is 0, the output is 0, so f of a is 0, right? Let's take a look at some mathematical examples so it kind of makes sense instead of all these words. All right, let's take a look at the remainder theorem, right? So let's say I have some polynomial, right? Polynomial. Maybe something like 2x squared minus 7x plus 3, all right? Now, let's say you get a question such as, find the remainder when the function is divided by x, x minus 4, all right? X minus 4. So, all right, so x minus 4. So the factor is supposed to be x minus 4, and we want to, now we could do the long division. That's not necessary, right? It's just asking for the remainder. So what do? For x minus 4, what's the root of x minus 4? Right? X minus 4, right? I'm going to set it equal to 0. I'm going to get x equals 4. So this is what I'm going to do. I'm going to plug in f of 4 into the equation. So 2x squared, not x squared, wherever I see x, I'm going to replace with 4. 4 squared minus 7 times 4 plus 3. So 4 squared is 16 times 2. 7 times 4 is 28 plus 3. All right, so I'm going to get 32 minus 28, which is 4. 4 plus 3 equals 7. All right, so my remainder here is, right, I could say f of 4 equals 7. That's my answer, right? That's my remainder, right? Or you could write out the remainder is, the remainder is 7. All right, now, easy enough. Now, can we say x minus 4 is a factor? No, we cannot, because it's only a factor if the remainder is 0. Here we got a remainder of 7. That means it's not a factor. Now let's take a look at another example, a graphing example with the remainder theorem. All right. Let's say I have an equation. Let's say 4x cubed minus 2x squared plus 6x minus 3, something like that. All right, let's say I have this equation here, all right, and then they ask you, right, let's say g of x equals this equation. Now they ask you, is x minus 3 a factor? Right? Is x minus 3 a factor? Well, how would you do that, right? Okay. Well, what you would do is the same thing, right? Factor and remainder theorem, they lend themselves into each other. So the 0 for x minus 3 is, I'm going to set this equal to 0, right? And I'm going to get x equals 3. So I'm going to plug in 3 into the equation, into g of x. I'm going to plug in g of 3 equals 4 times 3 cubed minus 2 times 3 plus 6 times 3 minus 3. All right, so 3 cubed is 27, 4 times 27 minus 2 times 3 is 3 squared, so 3 squared is 9, so 2 times 9. 6 times 3 is 18 minus 3. So we're going to 4 times 27 minus 18 plus 18 minus 3. So the plus 18 and minus 18 cancel out. I get 4 times 27. It's going to be 108 minus 3. I can confidently say not a factor, right? Not a factor. Because 108 minus 3 is going to be a very, very large number. It's going to be 105, right? So I'm going to have a remainder of 105. Right? If I have a remainder of 0, that means it's a factor. Now, let's say you're asked a question like this, a graphical question. Let me change colors. Let's say you're asked a graphical question, such as, all right, let's say they give you a graph. They give you a graph of, all right, 1, 2, 1, 2, 3, 1, negative 1, negative 2, negative 1, negative 2, negative 3. Let's say they give you some function like this. All right, so then they ask, what is the remainder when, let's call this, I don't know, h of x. When h of x is divided by x minus 2. All right? So x minus 2, right? That means the 0 here is x minus 2 equals 0. I'm going to solve for x. X equals 2. All right? So I'm going to look at where x is 2. X is 2 right here. X is 2 right here, right? This is where x is 2. Now it's asking for the remainder. All right? So I'm going to go up all the way up to here. Right? This here, the output, the y output, is the remainder. So on the graph, you can see the remainder, all right, as the output, right, of y, right? When you look at the coordinates, right, you can see this as the remainder. Now this is somewhere between 2 and 3, right? So the remainder when h of x is divided by x minus 2 is going to be a number between 2 and 3. Let's estimate, let's say it's about a little over half. Let's say the remainder, I could say h of 2 equals, let's give an estimation of 2.6, all right? So that's the remainder, right? You can find remainders on the graph. The remainder is your output. The remainder is your y. So y values are your remainder when a polynomial is divided by x minus c, right? So that's the remainder, all right, your y values. So if it gives you a graph and it asks you what is the remainder when it's divided by x minus 2, you find the 0, right? And you say what the remainder is, right? Let's do another example using this graph, right? Let's say they ask, find the remainder when h of x is divided by 2x plus 1. All right. when h of x divided by 2x plus 1. All right, first thing you're going to do, right, you got to find what this is on the graph. What's the x value, right? So I'm going to plug in 2x plus 1. I'm going to find the 0 here, equal to 0. I'm going to subtract 1 on both sides. I'm going to get 2x equals minus 1. And I'm going to x equals negative 1 over 2 or negative 0.5. All right. So I'm going to find where x is negative 0.5, which is, I'm going back to the graph, which is about right here. Right? Now I'm going to go all the way up. Right? Go all the way up. This, to me, if we do an estimation, is something like 1.8. So I could say h of negative 1/2, right? That's the 0 of this factor. H of negative 1/2 equals about, right, we're estimating 1.8. All right, so that's how you can do the question graphically. All right, one last one to tie this off, really easy. Let's say you have something such as, let's say they give you a table, right? Let's say this is a of x, and the table, your xy table is negative 1, 2, let's say 0, 5, let's say 1, 0, 2, 3. Okay, and they ask you, all right, what is the remainder when a of x is divided by x plus 1, right? So again, you find what x is here. You set x plus 1 to 0, right? You get x equals negative 1. All right. Remember, your remainder is your output. What is my output when x is negative 1? All right, let's take a look at the input-output here. It's 2, all right? It's 2. So I could say f of, or a of negative 1 equals 2.